Good evening. My name is Bruce Campbell, and I'm the newly elected president of the Fort Worth Astronomical Society. And, oh, well, thank you. I am very pleased to be in this position, but as my first action, I wanted to recognize the man that's sitting in the back row, Robert Circus, the previous president. Yeah, a round of applause. I think it was important to recognize his service over the last 2 years. He was instrumental in getting the build out of the dark sky site that we know as Rising Star Observing Area. Plus, he started several outreach programs that are unique and very positive for the club. So I was going to recommend a round of applause, and would it hurt to give him another one because he served 2 years? Good. Thank you, Bob. So I am so glad to see so many people here on All-Star Week. I know where your priorities are, and I'm happy to see that. So, thumbs up. I think we have a great show for you tonight, program for you tonight. But I did want to mention, anybody that hasn't signed the attendance sheet, be sure to do so at the break. I think that's important. So let's go to the next slide. Okay, before I call for any visitors, I want all the visitors to know that we already have something in common. Nearly everyone here experienced what you're going to experience tonight, and that is it's your first meeting at the club, or you just became interested in astronomy, or you're about to buy your first telescope. All of us have done that. And so do we have any visitors? Oh, hey, yep. So,
kind of, but I have actually been a member before. I've actually been a member a couple times before, but I've been out for maybe about 7, 8 years. When the kids were younger, it was kind of hard to kind of keep up with stuff. But now my son is starting to show some interest in astronomy. He's even talking about becoming an astronomer someday. So we're trying to get back in. My name is Garrett, by the way.
okay. Okay. Well, with an 8-year absence, I think you'll notice that quite a few things have changed. We've moved into the 21st century, and everything is going really well. Okay. Anyone else? Any other visitors? Okay. Let's go to the next slide. Okay, so these are the new folks that have joined the club since our last meeting. Are any of those folks in the crowd tonight? Hey, great. Welcome to the club. And could you identify yourself?
We're the Johnsons.
Excellent.
Stephen and Jude.
Okay, welcome. So I encourage everyone here at the meeting during the break to stop by and welcome the Johnsons to the club. All right, let's go to the next meeting, next slide. So about FWAS, kind of interesting. We were founded in 1949. Currently, we have around 380 individual members. There's a wide range of experience. We have a diverse group of astronomers, anywhere from the professionals to the beginners. You'll find that most of the astronomers are willing to help you out with issues. And we are a nonprofit, so what does that mean? You can donate to the club. Let's go on. So look at our resources for those who are visiting. These are some of the things that we have. And this is my take on the benefits of joining the club. Number one, you do have access to a diverse group of astronomers who have the combined astronomy experience of thousands of hours. So if you have a question, we can probably answer it. If you've got a problem, we have one or more solutions. And then you'll also find out that any mistakes you make, we've already made them. So we can help you out. The second thing is if you're interested in staying up to date on club events or astronomical things that happen, or you want just to keep in touch so you can ask questions, you should sign up for the e-group, which is our discussion forum for astronomy. That's the second benefit. And then the third benefit, in my mind, is our dark sky site. And that's what we call Rising Star Observing Area. It's about 2 hours west from this building. And you can escape to dark skies that is with a little light pollution, but nothing near to what we experience in the DFW area. So that's number one. Plus we have club telescopes. We have a loaner program where you can check out a telescope for an extended period of time and then return it. That way you can test the scope to see if that's what you really want to get into. Our inventory of loaner scopes consists of Dobsonians, but we plan to add Schmidt-Cassegrains in the near future. We also have the membership handbook and some other online resources, which is pretty cool, like YouTube. If you miss a meeting, you can always catch up. And the website, which is slowly being updated with more current information. Next slide. Oh, and there you go. And there's your online resources. This presentation will be up on YouTube in the next couple days, so you don't have to write them all down. Oh, we're live. So it's being recorded as we speak. No do-overs. All right, next slide. And I'm looking at Bill Hall, who will introduce tonight's guests.
Thank you. Okay, so our guest tonight is Dr. Tyler Richey-Yowell, right? I got that right? And she's with Lowell, oh my gosh, I misspelled your name, I'm so sorry. Yowell with Lowell Observatory. that was a test that I failed miserably. Anyway, yeah, so she studies stars, the evolution of stars that are smaller than ours, and how the evolution of those stars, how they work and how they evolve and how they affect the planets that orbit them, and thusly what sort of life, habitability could happen. So take it away, please. Welcome.
Thank you. All right, let me get stuff set up here real fast. All right, can you guys see all that and hear me okay? All right, getting a thumbs up. Cool. Well, I am Dr. Tyler Richey-Yowell from Lowell Observatory. And thank you guys so much for having me. I saw some Eclipse Over Texas shirts as you guys were setting up. And I was down in Waco for the eclipse, and that was about the time where you guys reached out, and so it's like, yes, more Texas astronomy, let's go. So, and I'm going to be talking to you tonight about the work that I've done over the course of my PhD and into my postdoc here at Lowell. About understanding K-stars and how they evolve, primarily the UV and the X-ray and how those evolve. And so while this is interesting in and of itself, the big question for me is, what does this mean for planetary habitability? So my perspective on the potential habitability of planets around these types of stars, these K-stars, has really changed a lot during my time studying them in the past, I guess it's in 7 years now. And so I want to kind of lead you guys through my experiences and kind of have you guys learn about this in the same way that I learned about it. Because I think it's fun, the whole path of discovery, and we need to remind ourselves that science is a process, and it's so much fun when we learn new things. That's the most exciting part to me. So, yeah, all right. So first off, I want to make sure that we're all on the same page about what a K-star is, but also what M and G type stars are, since I will also be talking about those a lot as well. So M stars on the left here are the smallest and coolest types of stars that make up 72% of all stars. And those can be broken down, if my slides go, there we go. Those can be broken down into late type M stars, or the smallest and coolest types of stars that there are, and early M type stars, which are a little bit bigger than that. And the difference between these two is that late M stars are fully convective, meaning they work kind of essentially like giant convection ovens. And early M stars are partially convective and partially radiative, meaning they're basically part convection oven and part microwave, kind of. And I point this out only since because of these differences in their makeup, their properties can be somewhat distinct from each other. And so you'll see in the rest of my talk that I talk about early and late type M stars. And so that's what I'm referring to. Just remember, late is the smallest and coolest type of stars there are. All right, so that's M stars. And on the other hand, there's G-type stars, or essentially stars like our sun. And these make up about 8% of all stars in our galaxy. And K-stars fall in the range between these two. And so a lot of work that has been done for searching for a potentially habitable planet has really focused on M stars because they're so small that they have a really high planet to star mass ratio or radius ratio, which means they're really easy for us to go and study and characterize. And also in terms of studying the potential habitability of planets, people have really been looking at G stars because obviously we have one detection of life here. But K stars have often been neglected in these studies. And so, yeah, that's why I have started studying them. And I want to take a second before we get into this to have you guys think about something. So I can't quite see how many people there are and your faces. So maybe just to yourself or maybe the people, I guess I can't really even see the chat right now either. Okay, think to yourself, okay, where do you think we'll find life? Is it going to be around a sun or around a star like our sun? Is it going to be around a star like these M stars, these tiny cool stars that are easy to characterize, or around a K star? And don't let the name of this talk bias you. Yeah, so just think about that for a sec. And if someone wants to shout something out, that'd be fun to hear some opinions, but we'll take a few more seconds to let you think. Because I'm going to ask this a few times throughout my talk and see if your opinions change, since mine certainly did. And so when I've given this talk before, this point I get pretty much evenly split on FG or K, of GK or M stars. And so I'm willing to bet that's probably about what you guys are thinking. All right, so let's get into the talk then. So how do we actually go about finding life? So ideally, if we had unlimited time and unlimited resources, we'd search for life like this. We would discover a rocky planet, and we check to see if it's in the habitable zone, which just means that it's at the right temperature distance from the star where the water would be liquid. And then if it is in the habitable zone, we go and look at it and measure it and see if there's any molecules that would be indicative that life is there. Pretty easy, right? Well, in reality, it's not really feasible for us to observe every planet that's out there. We have to have some way to prioritize which planets we want to actually spend the time on. And so like right now, we have over 5,500 exoplanets that we know of, but it's estimated in the next
2 decades, I believe, that we will be up to millions of exoplanets with the new NASA flagship missions that are going out. And so that's a lot of planets to go through. So that's why we have to be able to prioritize and figure out which ones do we actually want to spend the time observing. But true habitability is a very, very complicated puzzle. And so the major components that go into this are the effects from the star, the components of the planetary systems themselves, and the properties of the planets themselves. And of course, each of these can get broken into further subcategories that each of them play a role. And so my research is really over here on the left here, this spectral energy distribution, which essentially just means we're understanding the spectra of these stars. So how much light of every color is being emitted by the star, and also the stellar activity. So that's kind of like, think of the flares that we have on our sun. And then also the luminosity evolution. So how does the brightness of the star change over time? And so this all combined really tells us how much radiation would be incident on a planet over time. And so to rephrase this, in order to understand planetary habitability, we need to know how much radiation of the host star, or sorry, how does the radiation that a planet is receiving from its star change over time, and how does it evolve? And some of the most important wavelengths for determining planetary habitability are these at these high energies, because here's where you can cause photochemistry to occur in the planet's atmosphere. So really, you're breaking down molecules, and you can even damage DNA. We go outside and we have to put on sunscreen to protect our body from the sun's ultraviolet radiation. And when you go to the dentist, and you have to get your teeth x-rayed, you have to wear those lead bibs to protect the rest of your body from the x-rays. So we kind of get a sense already that these are even bad for life, but they're also bad for planets as well. And we break down the UV into 3 different wavelength regimes. So if you're still thinking about sunscreen, think of like UVA, UVB, UVC. In this case, we're referring to these as the near UV, which is closest to the optical, the far UV, and the extreme UV, which is almost to X-rays. And so what I'm going to be talking about for the rest of this talk is really the near UV, the far UV, and X-rays. And the reason we're not really talking about extreme UV radiation is because it's extremely difficult for us to measure, and we can only study the closest systems to us, because actually the interstellar medium between stars absorbs a lot of this radiation. So it's really difficult for us to observe. So we're just going to focus on the near UV, the far UV, and the X-rays. So what happens at these wavelengths is that the UV will photodissociate, so break apart molecules that are necessary for the development of life, such as oxygen or water, or signatures that could be indicative that life may be there, like methane or ammonia or nitrogen oxide. Whereas the X-ray and the extreme UV will ionize or strip away electrons from the atoms, and it can actually cause complete erosion of the atmosphere in a few million years, which is not good if you're trying to live there. You want an atmosphere. And some of you guys may have actually seen in the news that there was this really cool press release from the James Webb Space Telescope recently that discovered the first evidence that radiation from a star is directly causing the atmospheres of exoplanets to change. The James Webb Space Telescope, JWST, recently looked at WASP 39b, which is a Saturn-like planet around a Sun-like star. And they saw a clear signature of sulfur dioxide in the atmosphere, which, for the amount that they saw, means that it had to go through a process where UV radiation comes in and breaks apart the water molecules in the atmosphere. And then those kind of break down further, recombine with some other stuff in the atmosphere, and you get sulfur dioxide. But the only way that you can even get enough of the sulfur dioxide is if your water is constantly getting broken down from the UV radiation and broken apart from the UV radiation. So we now know for certain, it's not just theoretical, that the high energy radiation is actually shaping and rearranging and changing exoplanet atmospheres. So what we really need to know to understand planetary habitability is how this stellar high energy radiation evolves during a timescale when these planets are forming and their atmospheres are stabilizing. But then there's the question of what kind of host stars do we want to look at? Well, there's this group, Kuntz and Guinan, who made this paper in 2016, who determined a parameter called the habitable um, real estate parameter. That's what it was called. And so this is a plot showing the probability of habitable planets, with higher being better, as a function of essentially stellar type, or what the temperature of the star is. And anything above Earth here is considered super habitable, so having a higher potential for habitability than even Earth had. And so you'll notice that pretty much everything to the right of the Earth here has a higher probability than even Earth had. And you'll notice that this really it peaks over in the right in these late M stars here, the coolest M stars. But we've recently seen that there's M stars kind of have a problem going on. So not only do these M stars flare more often than our sun, they exhibit super flares, or flares with larger energies than the largest solar event ever recorded, the Carrington event. And that actually happens once a day on some of these stars. And so these flares are actually dumping a whole bunch of UV and X-ray radiation into these planetary systems. And that might not be good for planetary life, because we've seen that, this UV and X-ray is breaking apart the water, for example. So not super great if you're trying to have life form there. So that might rule out the M stars. So where is the next peak? Well, that's over here in this K star regime. And you'll see that everything within the K stars, the yellow box here, is above 1. So it's we still think of it as super habitable. But we don't really know at this point what the high energy radiation environments around these types of stars look at. And so that's where I come in. So I wanted to know what the high energy evolution of K stars looked like, and I expected it to fall somewhere between G stars and M stars. So for G stars, or stars like our sun, when we look at the X-ray evolution over time, this is basically how much radiation there is and what the age of the star is. So when we look at this over time, we see that there is a constant decline, and this is happening after about 10 million years for stars like our sun. And there's no constant period of flux. It just declines pretty much right away. And then if we look at the M stars, particularly the early M stars, so we've looked at these in the X-ray and the UV, and we see, if we just look at these red points here, we see, yeah, there's kind of constant activity, kind of a high level of flux for a while, out to an age of 150 million years, and then it starts to fall off in time. And so it would make sense that K stars probably, they're maybe constant out to, we'll say, maybe 100 million years, and then they start to fall off because their properties lie in between G stars and M stars. So it makes sense that they act similarly between G stars and M stars. So that's what we were kind of going into this project with the idea of. And so this is where I started the Habitable Zones and K-star Activity Across Time project, HAZCAT, which, if that sounds weird, it's because it's an extension of a project called HAZMAT, which makes a lot more sense. It's the M-star Activity Across Time project. And so the goal of this project is to measure the activity evolution. So measuring the near UV, the far UV, and the X-ray fluxes, or the radiation that's coming from these stars, of K-stars specifically, over stellar ages where the planet atmosphere is developing. So basically while the star is still young. Yeah, so this is the main goal of this work. Measure how the UV and the X-ray evolves over time for K-stars. All right, so this is one of the evolution plots for K-stars in the far UV. And I'm going to use this plot just as an example to describe to you what kind of data we have, and then we'll go from there. So this is the far UV flux as a function of stellar age. And so let me, and sorry, this is also the flux excess. So let me first explain what we mean by excess. So here's a plot of the outer atmospheres of stars. And from the surface outwards, we have the photosphere here, the chromosphere, the transition region, and the corona. And so the wavelengths that we're interested in, the UV and the X-ray, mainly come from these outer layers. And so the X-rays are mostly coming from the corona, the far UV from the transition region, and the near UV predominantly is coming from the chromosphere. And part of what we're interested in here is understanding what the evolution of each of these layers of the stars look like. Yes, what is, and then part of, but the photosphere, the surface of the star itself, is also emitting a very small fraction of the total UV and the X-ray. And so we want to actually get rid of that and subtract it out so we can see just what is happening at each of the outer layers of the star itself. And that's what we're calling the excess, really the outer part of the star. Only, not including the photospheric contribution. All right. So it's back to this plot. Each of these red points that you see, or the white triangles, are measurements of individual stars. And for the UV data, this is coming from GALEX, the Galaxy Evolution Explorer, and the X-ray data is coming from ROSAT. And so the circles are direct measurements, while the triangles are limits, where we didn't fully measure, but we can get an estimate of what the signature should be. And so you can see that we have hundreds of observations going into each of these plots. But a simpler way to look at this, though, is to find the median per age bin. So these blue points here that you're seeing are actually the median of each age bin. And the error bars that you see aren't actually error bars. They're actually what we call the interquartiles. So basically where the middle 50% of the data lies. Yeah, so remember this is just the medians here in the blue. So this has kind of been a whole primer just on this plot. But what I want to do now is to take these median values of each of these plots and plot them on their own. So this is the same plot that you just saw. In this case, I've converted from flux density to flux, so that's why the numbers are different, but that doesn't really matter. The shape should be the same. It's essentially the radiation from the star. And this is the median of the far UV and how that evolves for K-stars. And here's what it looks like when we add in early M stars, by which I mean the hotter or bigger M stars. They're still smaller than K stars, but they're kind of one step down. And they appear to remain elevated for much longer before declining pretty rapidly. And if we add in the late M stars, or the coolest or smallest stars there are, excuse me, then we see that those stars, these squares here, remain pretty much at a constant flux and don't really decline much at all. So they remain active for longer. And so these might look a little different, but you can see that really this difference is only a factor of 10 from each other in order of magnitude. So they're really not that different overall. And now I'm going to throw in what this looks like for the near UV and the X-ray for M, K, and for K stars, early M stars, and late M stars. And right about now, I bet you're probably thinking, wow, there's a lot of lines overlapping on this plot. That's making it very hard for me to understand what's going on. But that is exactly what I want to point out, that these lines are all right on top of each other. And so the point here is that the intrinsic UV flux from these stars is similar, that they are all right on top of each other. So what does that mean for planets in the habitable zone? So if the fluxes coming from the star are similar, um, then we have to think about what that's going to be at different distances. Because the habitable zone is basically defined as where, or as the temperature of the planet where water would be liquid. And so you can kind of think of stars as giant campfires. So for stars like our sun, they're relatively hot. So the habitable zone is somewhat far away from the sun at a distance that we define as one astronomical unit, 1 AU. But K-stars are kind of like smaller, cooler fires than the sun. And so the habitable zone is going to be a little bit closer in at 0.8 astronomical units. And early M stars are even smaller and cooler, so their habitable zone is closer in. And then when you get to the smallest, coolest fires, these late M stars, we kind of have to be huddled in very close to them to get any warmth. And so the late M stars have a habitable zone distance only about a tenth of the size or the distance from the sun to Earth, so 0.1 AU. And so the radiation from the star drops as a function of distance. And so if if all of these stars are emitting the same amount of UV flux, that means that because the habitable zones around K stars are further away from their host stars, they're receiving less UV and less X-ray radiation than the M stars are. So from this paper, we saw that the UV and the X-ray flux from K-stars is similar to M-stars, which means that in the habitable zone, those planets are going to be receiving lower UV fluxes for those around K-stars. And this is just because the habitable zones are farther and wider out. So this makes K-stars more suitable environments for detecting life than M-stars. All right, so how are we feeling about K versus M stars? I want you to take a second and think about that. Probably a little bit more favorable to K stars than M stars now, I'm guessing. Yeah. That's usually what I see when I've given this talk before, so keep thinking about it. So the results from that first paper were really good general start to this work. However, the GALEX data, that UV data, is all photometry, which is essentially broadband and gives you a general picture of what's going on in the star, which is a great start. But we want spectroscopy of these stars as well, essentially getting the details from the star. So below here, at the bottom here, is a spectrum. So how bright the star is as a function of what wavelength or what color of light. Each of these lines here that you see sticking out kind of above this continuum here represents a emission from a certain molecule, a certain atom, essentially. And these actually go and trace out different parts of the star. For example, the near UV, you have the magnesium 2 line, which is formed in the middle of the chromosphere. And then for the far UV, that's mostly tracing the upper chromosphere or the transition region of the star. So yeah, so through each of these, we're actually going and kind of very specifically measuring certain stellar heights of the star rather than just getting a broad picture of what's happening at each of these levels. We're kind of getting more and more detail with these spectra. And so by understanding the evolution of each of these specific lines, we can see the evolution of different stellar regions. And so we've seen in previous works from my team that the UV evolves considerably between young to field or old-aged stars. So in this example for M stars from Park Lloyd in 2021, if you look at, this is again brightness as a function of wavelength or color, and so the youngest stars are in blue here. The median age are orange, and then the old stars are in green. And you can see that there's a clear evolution here. The stars are essentially dropping off in light as they get older. And this is actually happening on the several orders of magnitude. So it really actually does start to play a role in affecting planetary atmospheres. But at this point, there wasn't any spectroscopic UV data of K-stars at these ages. And so obviously I was all over that and wanted to study it. So I led a Hubble Space Telescope proposal with some awesome collaborators at Arizona State University, University of Arizona, and University of Washington. And we were awarded 73 orbits to study K-stars at different ages, both in the near UV and the far UV. And our goals were to spectroscopically study the evolution of activity, and also determine flare frequency distributions, which essentially just means how often flares of specific energies occur, and also to model the extreme UV spectrum. Because remember, we can't go and measure that, but if we could kind of get the UV details, we can understand what that spectrum looks like more. But today I'm really going to be talking about the first point here. So spectroscopically studying the evolution of activity. All right, so here are 3 examples of spectra of stars, of K-stars, at 3 different ages: a young in blue, an intermediate age in orange, and an old star in green. And so if we go back to what the M stars look like, I want you to look at the blue and the orange, the young and the intermediate. There's basically no difference between these spectra here, whereas for the M stars, there's clear evolution. They're definitely separate. And so as well as comparing just this broadband characteristics, we want to look at what each specific one of these lines is telling us and how that evolves itself too. And so if we take magnesium-2 here, for example, we can measure the flux of the radiation from each line and plot this as a function of age. And these flux evolutions are typically presented as a region of constant flux followed by a decline. And we can see here for magnesium-2, this decline isn't really that sharp. But other than magnesium-2, we've done this for all these other lines out here that are tracing different parts of the star and telling us what's happening at each of the different layers of the star. Oops. And what's really interesting, though, is that when we compare what we see for M stars in the black here, or sorry, what we see for K stars in the black here, to what this evolution looks like for M stars in the red, you'll notice that all of our intermediate age points have not declined whatsoever and are still quite active for the K stars, whereas the M stars would have been lower by this point. Is same for the older stars as well. All of our stars, all of our older stars are, except for this guy over here, all of our older stars are much higher than or have more flux than what the M stars were showing. So I don't want to overwhelm you with a ton of plots. So I've just shown a subset of some others here. And so you can see that this is true for other lines as well. That generally our K stars have more flux than for the M stars. Another important factor to look at, though, is how the UV changes with rotation period. And so instead of age here, we now have rotation period, which typically corresponds to age. So they should look similar in terms of having a flat kind of high activity for a while, and then it slowly falls off. And we see that for the far UV lines, that this actually matches up much, much better for between K and M stars when we're looking at rotation instead of age. And this is still kind of matchy. It's a little farther off, but yeah, so we see that the rotation is matching up, but the age really isn't. And so that was a little bit confusing to us. And so I was kind of wondering what is happening here. And so we think this actually might be related to this really cool recent discovery about K-stars. And so from this plot here, is showing rotation period for stars as a function of the temperature of the star, what type of star it is, which is written out here more. And so overlaid on top of here. So basically, these are all points of different ages. So all the blue points are about 120 million years old, orange 670, green 1 billion years old. And so this is kind of telling us what the rotation of stars are as a function of age. And all these lines here are where we would expect from current models, where we would expect all of these points to fall. All right, and what I want you to look at here are the orange and the green points. So over here for G stars, we see that the orange points and the green points are pretty separate. So between 670 million years and 1 billion years old, these stars are evolving. They're slowing down over time. Their rotation is slowing down over time. But if we look over here at K stars, these points are again right on top of each other, and so there's no rotational evolution between these ages, and they kind of stay at the same period of about 10 days. And so this actually might be what we're seeing in why the UV appears to be active for longer in time, but the rotation kind of remains the same. And so since we know that the rotation is tied to the magnetic field and therefore the magnetic activity of the star, which the UV is magnetic activity. And so while we see the age evolution, or we see that the age evolution happens sometime between 650 million years to 5 billion years, and the rotational evolution declines after about 10 days here. And so basically what's happening is these stars are essentially spinning down. They're rotating more and more slowly over time, but then they stay at the same rotation rate for a while, which means the same level of activity for a while, and then they continue on in their evolution. And so that seems to be what's happening, and it's because these stars remain rotating more quickly for longer than we expect, their activity is also remaining high for K stars longer than we expect. So in summary, the K-dwarfs appear to be experiencing a prolonged period of saturated or high raised activity compared to M-stars, leading to larger UV fluxes than even the M-stars have. And this is consistent with a really cool new independent study. So we seem to think that, yeah, these things are related, and so it makes sense that they're larger in this case. But it was not expected at all by either group. Yeah. So reviewing what we've done so far. So the first project showed that K stars have similar UV fluxes to M stars. And then the study from the Hubble Space Telescope showed that K stars have higher UV fluxes than M stars. But these results aren't similar. So what was actually happening here? I was kind of banging my head against the wall going like, what is going on here? This is not what we saw before. These results should be the same. We should just be getting more detail out of them, not that they're changing entirely. And so I realized during this process that the question was not actually or that the actual question wasn't actually about comparing the results, but kind of the methods that I did the results. And so actually when I did that first study that I showed with the GALEX data, the problem is we didn't actually have any distance measurements back then. So this was about 2017. And so in order to kind of estimate and put everything on the same page, because a star that's farther out it might look dimmer than one that is closer, and so we really need to know the distances in order to understand what is actually getting emitted from these stars. And so to do that, we divided by the J-band magnitude, which is an infrared magnitude that's supposed to be constant in time and not change at all. And it's a nice, easy metric by which we can say okay, we can estimate for the distance that way. Whereas when I was looking at the Hubble Space Telescope data, I was just looking at the UV fluxes. We got the distances at that point, and we were able to precisely correct those. And so basically, it came down to what's the only difference between this is the J band. And so we had assumed that these were going to be constant in time, but when I actually looked into it, it turns out that it is constant in time for the K stars, but not for the M stars. So it wasn't really comparing apples to apples. And so I, at this point, went back and redid the whole first project that I showed you, but this time we had the amazing new Gaia data. So Gaia is a telescope that takes very, very precise measurements of stars and their motions, and are able to calculate very, very precise distances to stars. And so that had come online between now and then, and we had all the distances now. And here's what this looks like. So this is the same exact plot that I showed you before. This is the near UV flux as a function of stellar age. And then remember how all those lines were on top of each other before? So this is what it looks like now. So you see that for the K stars, it's clearly above the early M stars and the late M stars. And you'll notice that the early and late M stars fall off pretty quickly compared to the K stars, which are still elevated for a longer period of time. And you can see here in the far UV that this is actually about almost to 1 billion years before these stars actually start to decline. And so by the time you're about the age of our sun, about 5 billion years old, yeah, you're 15 times larger than your K-star flux is about 15 times larger than both the early M stars and late M stars. But what we really want to know, though, is what the flux in the habitable zones of these planets look like, or around each of these types of stars. And so if we take the intrinsic fluxes that we see, so what's coming out of the star itself, and say, okay, well, let's move that to a distance, let's look at the distance from the star that the habitable zone is. What would the flux in the habitable zone be? What would that planet, how much UV or X-ray would that planet receive? And so in this case, if we recalculate the fluxes for the distances of the respective habitable zones, we see this. And so we see now the flux in the habitable zone are all actually very similar. So what we've learned is that there actually isn't a big difference in the UV radiation between a K star and an M star habitable zone planet in both the near UV, and this is what it looks like in the far UV as well. And so while the K stars have primarily been touted as these Goldilocks host stars, mainly by me, because after the first project, I was like, yes, they have so much lower UV radiation in the habitable zone. It doesn't, or we should really be looking around K stars, not M stars. And then I saw this and I'm like, oh, it doesn't really make a difference. They're both about the same amount of UV and X-ray radiation. So there's really no advantage in the UV for K stars compared to M stars. They're about the same habitable zone fluxes. What's interesting, though, is that in the X-ray, we do actually see a pretty noticeable difference and a lower amount of X-ray flux in the habitable zone, at least compared to the late M stars, the coolest M stars. So this is about a factor of 10 difference here. And so comparing all of these, the near UV, the far UV, and the X-ray, you can actually see that there's almost kind of like a difference in how all of these evolve. So like the M stars seem to pretty consistently fall off after about 150 million years. But like within the error bars, these are like this is pretty flat. Whereas like there's not really an age of or a strict point where it seems like it starts to decline. Whereas for the far UV, Yeah, this is flat and then it decreases. Pretty clear. So that's after about 650 million years. And then the X-ray, like this has already started falling off by this third point here. So that's after only about 45 million years. So there seems to be a wavelength dependence to the at what age these K stars start to decline in activity. That's not showing up for the M stars. All right, so these are all comparisons between K and M stars, but I guarantee there's at least one person in the room thinking, but what about stars like our sun? Well, unfortunately, there's no really direct comparison study at this time for stars like our sun in the UV, but there has been an X-ray and extreme UV radiation measurement from 2005, where we can kind of estimate. And so in this case, my best guess is that the sun would actually be a bit lower on this plot. And so you would actually have about the factor of 10 times lower far UV radiation. And then for X-rays, because we do actually have something to compare, we know that this essentially corresponds to this on this point. So again, a factor of 10 lower radiation. But to tie this back to our big question about planet habitability, what does this mean for the planets around K and M stars? Well, the higher UV activity, at least compared to stars like our sun, means that habitable zone planets around habitable zone planet atmospheres are probably going severe photodissociation. That means breaking apart of the molecules, breaking apart of those potential biosignatures such as water or methane, or the molecules that are necessary for life to form. So probably not super great. But for planets around K stars, because you have lower X-ray radiation on the habitable zone planets, that means there's less heating in the atmosphere of those planets, and so you're probably not going to get so much heating like the M stars can, where they can actually lose their atmospheres. For the K stars, they're more likely to maintain their atmospheres, so there's a better chance there at least. All right. So, in conclusion, the work that I presented here has been some of the first UV studies of K stars, which was really, really fun to do. And in this process, we've seen that K stars are weird. They show a prolonged period of saturated activity, so high elevated activity, that isn't seen in M stars or G stars. And when you look at the flux incident on a planet in the habitable zone, you see that these planets receive similar UV but lower X-ray fluxes compared to those around M stars, which means that there's no K-dwarf advantage in the UV compared to M stars, but yes in the X-ray. But overall, it is looking like G stars do have lower amounts of both of these. So now I want you to go back to this question and think, okay, have my opinions changed at all? Because mine definitely did. Because I was first going around saying how K-stars are the best, we should all be looking at them. And now I think they're the best for other reasons, because they're weird and I like that. But maybe not so much for most habitable. And then, yeah, so I have one last thing to talk about. So that has been the research that I have been doing, and now I want to touch briefly on what was up and coming. And so, as I mentioned, things aren't really looking that much better compared to M stars, or for K stars compared to M stars. They seem to be about equally bad. So, but what will be the determining factor for planet habitability around M or K stars? What other factors do we really need to consider that can tell us whether this amount of radiation will actually be a problem or not? So if you recall earlier, I mentioned that M stars experience these huge super flares that happen once a day. And each of these flares is dumping a ton of extra UV radiation on the planet, on top of the quiescent emission, what's just constantly being emitted from the star, which is I hopefully mention this, but probably may have skipped it. So all the work that I've been doing so far has been on the quiescent emission, so what's just naturally coming out of the stars. We haven't really been thinking about flares so far. So one of the questions that we need to consider in understanding K-star habitability is what the flares look like and how often they occur. And I have a student this summer whose name is Noah Fernandez, who's a student at Northern Arizona University, who is doing just that. So if you recall, part of the Hubble Space Telescope program was to get data to study the flares. So all the spectra of those K-stars that I showed you are actually in what we call time tag mode. So it gives us the ability to create light curves that are, or basically how the brightness changes over time, that are simultaneous with the data that we got. And so here's an example of what these flares look like. So these are just brightness as a function of time, and you can see that there's some big peaks here that then fall off and remain elevated for a bit afterwards. So like this is a little higher than this, but really it's this big peak that we're interested in each of these, or two peaks in this case. And so what we want to do with this data is to essentially fill out what's called a flare frequency distribution. So essentially, how often flares of what energy occur. And so this is an example of what that looks like for M stars. So this is just saying that for M stars, the flares with smaller energies occur more often than flares with larger energies. And then young M stars have basically a higher amount of everything. And so we don't really know what this looks like for K-stars. It could be that these K-stars aren't flaring as often or with as large of energies. But this could also look like this, whereas the evolution isn't very fast between the two. Or maybe it's a totally different shape. We don't really know yet, but we're looking to find out. And so far, I've only talked really about radiation, but as I mentioned before, true habitability is a combination of so many other factors. And in fact, planets may even have magnetic fields that help protect their atmospheres. Excuse me, which uh, when you have a very thick atmosphere, it actually lessens the effect that the high energy radiation has. And so being able to have an atmosphere and keep that atmosphere very strong means that this high energy radiation wouldn't actually play that big of a role. It wouldn't be a problem as much. But the problem is that understanding magnetic fields on exoplanets is very difficult. So how do we measure those? It's a invisible force, really, and we can't just go and drop a probe there. Well, in order to answer that, we kind of have to think about the effects that magnetic fields cause. And so, because besides light or radiation, the sun is constantly emitting particles, which we call the solar wind. And magnetic fields essentially force these charged particles from the stellar wind off to the side of the planet, or instead trap them in the atmosphere of the planet, where those particles actually interact with the atmosphere of the planet and become auroras. So this is exactly what we have on Earth, and we've also seen this on Jupiter, on Saturn, on Uranus, and also brown dwarfs, which are objects that are between stars and planets in mass. And so the next step then would be, well, let's see if we can find these on exoplanets. And so another Lowell astronomer, Joe Lama, and I have been working really hard on trying to find these, and have been searching around hot Jupiters. So basically planets similar to Jupiter, but they orbit very close into their star and have years of only a few days. And this is what we saw in our search for this recently. So these aren't actually pictures, but for the sake of time, they're essentially pictures. And the white crosshairs are where we would expect to see a nice little blob that would be your planet. So unfortunately, we haven't detected auroras yet, but there's several groups out there, including my group, using multiple different methods. And I think in the next decade, maybe even the next 5 years, we'll actually be able to see auroras on exoplanets and actually begin to directly measure the magnetic fields, which would be super, super cool. So these type of magnetic field studies play in with the whole big picture of stellar activity and potential habitability of planets. But we have to remember that these are just small pieces of the puzzle that is habitability, and there's still so much to understand, which is super exciting to me. So yeah, so to add on to my conclusions, what's really going to make or break it for the K-star's super habitability is understanding the flares and the magnetic fields in these systems. And hopefully we'll make some very exciting discoveries really soon about these. All right, thank you.
Well, enjoy that can of worms there. Sounds like you've got a lot of work to do. Does anybody have any questions? All right. Hey, Bob, why do I keep calling you Bob? I keep calling you Bob. Can you help me with the, all right, here we go.
Well, thank you. I was closest to you. Thanks for coming this way, Bill. Thanks for the great presentation. This is really, really fascinating. My question is just a really simple one in terms of numbers. So you said there's
Yes.
to date about 5,500 exoplanets that have been discovered to date, and obviously with technology, like you said, in the coming decades, there'll be millions that you guys will detect. The simple question is this: for these K and M type, and go ahead and extend it to G type stars like our sun and so forth, how many of these exoplanets fall do we think within like a 0.8 astronomical unit in the case of the K stars, et cetera, or a 1 astronomical unit in the case of G stars? So how many have you guys determined are there that potentially at this point could be life inhabiting planetoids or whatever?
Yeah.
Does that make sense?
Yes, definitely. That's a
Thank
great
you.
question. So of our 5,500 exoplanets that we know about right now, there's actually only about maybe 24 that are in the habitable zone of their stars. Like there's enough that there's so few that they're actually all listed out on a Wikipedia article, just because there's only a few of them right now. But that doesn't mean that there's only a few of them out there. So the way that, so the missions that we have that have been measuring and trying to find these exoplanets, the predominant one has been the Kepler system. And it was not designed to study these types of, or it was not designed to find, there we go, habitable zone planets. It was just designed to discover any exoplanets. It was actually, fun fact, the Kepler telescope was actually proposed for before even the first detection of an exoplanet. So we were just trying to find any planet whatsoever. That has changed with the TESS mission. So TESS is the Transiting Exoplanet Survey Satellites. And it is designed to find habitable zone planets around M stars. And it has added to that. It's just slowly, we're still going through that data. It's still an active mission. And in terms of K stars and G-type stars, those are actually going to be, so it's easier to find the habitable zone planets around M stars because they're so close in that it's only taking a few days for them to complete an orbit. And whereas for, and we measure it by, we find these exoplanets by essentially looking at the dip in light when the planet transits the star. And so you see that once in orbit, or once a year for that planet. And so these future missions, such as the Plato mission that the European Space Agency is running, is really going to be, it's going to look for planets with longer orbits on the order of like 1 year. And so it's going to really add on to the number of planets that habitable zone planets that we know about. So that's sorry, that was a long answer. Essentially, right now we only have a couple dozen, but it doesn't mean there's more out there.
Okay, 2 quick questions. Number 1, how do you determine the age of the stars you're looking at? And number 2, are the technical problems with the Hubble going to affect your future research?
Ah, yes, great questions. So the first question is, how do we determine the ages of the stars? So these actually are, all of these stars are members of what we call young moving groups. So they're stars that we know were born together because they're all moving in space together. And they all have a similar composition, and they also have what we call youth indicators. Excuse me. So basically, signatures that only appear in young stars. And so people are doing their whole research projects just determining the age of these particular groups. And so we are very thankful for their data, so we can say, okay, this star is part of this group, so, and these researchers determine this has an age of 100 million years or whatever. That's really the only way we reliably know the age. Once you get to older stars, it's very, very difficult to tell the age, because something at 2 billion years looks almost exactly like something at 8 billion years old. So yeah, we're very thankful for the research being done with young moving groups, they're called. And the second part was, does the Hubble telescope problems affect my work? The answer is yes. Hubble's really, especially the UV systems, are really on their last leg. And within the UV community, we're all like, all right, this could die any second now. And they actually do have a checkbox on, like, when you're submitting a proposal saying, is this UV work or not? Because they really want to emphasize the ability, or Hubble's ability to study the UV. And so you actually get an advantage if you're studying the UV. And just because we can't do that from the ground, our atmosphere absorbs the UV, and so Hubble's the only thing until the Habitable Worlds Observatory, which should launch in 2045. But I mean, we all saw with JWST that took an extra 17 years. So who knows when it will really launch. Yeah, so it's really, Hubble could die any second, and we're all ready for it, really.
Anybody else?
I got it.
Oh, I see some online that I can repeat. So one was, how do you define habitable zone? So we actually we the field have a very naive interpretation of how we define habitable zone. We really only define it as where water could be liquid. So you're far enough away from the star that your water's not boiling off, but you also can't be too far where it would be freezing. And that's really the only thing going into defining the habitable zone. But as I kind of showed here, in this, like, there's so many other things that go into real habitability. And so it is a very naive way for us to interpret, like, it's not really habitable zone, it's water is liquid zone.
And on top of that, it's life as we know it.
Yes, exactly. Which, yeah, I mean, all of this, like, the UV radiation doesn't matter if your water, if you have some amoebas underwater, like, they're not gonna get affected by this as much, or if your life is in a cave. But I think that we really need to have a starting point with this, and it's easiest for us to find life as we know it. But there are actually people who are doing some really fun research of how do we find life as we don't know it, and trying to use actually, like, AI in order to look for signatures that, like, correlate with each other, and kind of work out if there's any patterns to things that we wouldn't have expected and looked for patterns. I don't really know the details on that, but there are people thinking about it, which is kind of crazy. Because then we know it, but then we don't know it. Yes. All right. And another question online. What's the principal reason why habitable zone planets are not found around other spectral types F through O? So I didn't really mention the other spectral types and just focused on stars like our sun and smaller. And those stars do have habitable zones, but it's going to be pretty difficult for life to form on those and planets around those stars. So F through O is bigger than the sun, and so for one, we have seen far fewer planets around those stars. We think just through the formation mechanisms, it's not as easy for planets to form. And also these stars, like as you get bigger, essentially they're burning fuel faster. And so these stars don't last very long before they die off. And like we've seen that life takes a while to form. It's been 5 billion years for us to get to the technological point that we are right now. And so if your star dies off before 5 billion years, the chance for finding life like us significantly decreases. So one, there's fewer planets. Two, the chance for life to actually develop into something that we could really be able to identify at this point it is unlikely. So that's why we really haven't been focusing on those at all. But that means, like, yeah, there are people who are studying that, and I think that it's great. And like we should be inclusive. There's also people studying life around, or the potential for life around like white dwarfs as well. And could life come up after the star has already exploded and now it's a white dwarf? And so basically the summary of this whole research is we don't know, but that's so fun. These are all small pieces of the puzzle. We agree we know nothing, right?
Okay.
Yes.
Can I ask?
Yeah.
Okay. Okay. I was thinking about pursuing my master's in, I think it's astronomical and planetary sciences, and I just wanted your input on, like, how was it for you, and like, do you have any tips and tricks for me?
Yeah. I think that it is a really fun field. I would definitely recommend when you're choosing where to apply, think about who your advisor would be. So I'd say that, like, I think any research can be fun as long as you have the right advisor, someone who will support you and guide you through the whole process really well. And the same for a PhD program as well. So yeah, like, reach out to the students who are working with that person at the time, and really just follow what interests you. Make sure you have a good support system as well with you. But it can be really fun, and really, it's just so exciting to be. The best part of astronomy research is that point where you're the only person in time, or like in all of history, that knows that thing about that star or that planet or that system. And that's mind-boggling to me, and it's so exciting. Like, that's the point I really like, and I just embrace that feeling when you can.
Very cool. Okay, well, thank you so much. We really appreciate it.
Yeah. Do I have time to answer one more question that's online?
What, online?
Or there's one more online?
I don't know.
I can read it out. I just wanted to make sure if there was time.
We do need to move along
Okay.
at some point,
Yes.
but we really do appreciate it. And
Yeah.
we love your enthusiasm about what you do, especially.
Thanks.
All right, thanks again.
Very good. So if you see the time on the clock, it's 8:20, so let's meet back here. Let's take a 10-minute break and meet back here at not 11:30, but 8:30. Thank you. Okay, cover your eyes. 3, 2, 1. Nova. That's good.
What's that? Oh,
All right. This is a good time to start the raffle. Thank you very much. So the first raffle ticket has been drawn. The winning number is 4807352. Once again, that was 4807352. Oh, we have a winner. There you go. Yeah. All right. Oh. Ticket number 2, 4807376. 4807376. No? I think so. Well, let's move on. And once again, 4807354. 4807354. Okay. Come on down.
Wait, I get another one? Wait, really? Okay.
Unless you ask one more question. Oh, yeah. Thank you. No, give it to. How many of these do we do? One more. This ticket number is 4807373. 4807373. Oh, Dwight. Great. Thank you. Is that it or one more? Yeah. Okay. That's it.
What do I want?
Take the best one.
What is this special issue?
Better mic.
Yeah. All right, sun's off. So this is everything that's in the sky for the next month. The blue horse head. So the cover picture here is Stephen Kennedy's recent image of the blue horse head. It's just amazing. Next slide. Just a really good shot. All right. So, bright comets in the sky this month. So we've got 13P Olbers. It's still brightening. It's magnitude 6.7 now in Leo Minor. And then 2023 A3 is in Leo. It is still brightening. This is the one. I thought it was Olbers and I was wrong. It was 2023 A3 is the one they're speculating could get as bright as 1 or 2 magnitude in the fall. It's falling apart. Okay. Oh, is that the one with the story where it's like we might be, it might be. Okay, all right. So we've got another. Jupiter. I think the sun got in the way this time. So it's another, whatever that comet was about 10, 15 years ago that was a big hype. Yep. By the way, this is the 30th anniversary of Shoemaker-Levy 9 running into Jupiter. So here's a little shot of that. I think there's a Hubble shot. Next slide. Occultations and close approaches. So there's one notable. These are always fun. Jupiter and Mars, very early morning on to dawn on the 14th of August is going to be 19 minutes apart. So really, really tight pairing there. That's about half the diameter of the moon there. This actually happens to be Spica right here. This is Patrick McMahon's image of the moon just about going in front of the star there. Next slide. So I got to talk about the sun because sun. And this is today's shot from Space Weather Live. You can use the app or you can go online, but it's an amazing resource. This is today's sun, and they do a shot of the disk where it shows what's going on the disk this particular day, and you can see all these sunspots. Enjoy this while you can, because there will be a solar minimum again. There always is. So the interesting thing is, so we're starting to see more sunspots near the equatorial region. They actually start as solar maximum goes through its cycle, that sunspot groups start to migrate towards the equatorial region. And let's go to the next slide here. And what it results in, if you graph that as if you didn't have enough graphs that you looked at today, that you get this thing called a butterfly diagram. And basically this is showing, you can see, they started doing this, Edward Maunder actually, who worked for the Greenwich Royal Observatory, started taking record of this in 1876. And he started graphing this stuff and started identifying that with every cycle, this 11-year cycle, that with every cycle, the sunspots would start appearing closer to the equator as the maximum went on. So it's a really fascinating effect here and not necessarily understood. So next slide. All right, and then there's T Coronae Borealis. I just want to remind you again, the star's about to blow up at any minute. And the cool thing is that Corona Borealis is straight up in the sky at night, so it's really great. Every time that I actually sit out in the backyard or something, you know, I just look at it for a while. It's like maybe I'll just see it. That'd be cool. But we haven't. But the thing is, it's magnitude 10.8 star, and when it blows, it's gonna become a naked eye visible star in the sky, which is pretty cool. So this is really any minute now. They're seeing the yes, sir. No, just at night. I mean, like magnitude 3 or 2. I mean, I think Polaris is like 2 or something. So it's not going to be naked eye visible. You'd have to be in the negative numbers for it to be naked eye visible, like big naked eye numbers. Next slide. So like I said about last month is double shadow transit season. It's cool. It goes through this cycle, and you get this usually every year. And in the rest of July and into August, you've got, you know, this is the first shadow that goes over, and then the second shadow that goes over, and you've got Europa and Io, and Io and Ganymede, and Ganymede and Io. And so these are all at nighttime. There are a lot more of them that happen during the day, but yeah, we'll celebrate this, because then I'll be able to use something besides the one picture I have with shadows on Jupiter. Next slide. Full moon. July's full moon is on the 21st of July, and that's Robert Cargill's handiwork there. Next slide. And then Mercury's in the evening again, greatest elongation, so it's going to be highest in the sky after sunset, and it'll be about 27 degrees from the sun, so it'll be high in the sky and highest on July 22nd. Next slide. And there's the Delta Aquarids meteor shower. I'll get to the other meteor shower soon enough, but this one is the one before it. It's Sunday night, July 28th, into Monday morning, July 29th. And, you know, when you're seeing this meteor shower and the other one, that you'll probably be seeing a mix. So it's kind of fun to look at, okay, so that one came from that part of the sky, and like knowing where the radiants are to know which meteor shower, which stream it's coming from. So this one, not quite as significant as the Perseids, but it's about 15 to 20. It's left behind by Comet 96P Machholz, or however you pronounce that. I'm not German. Next slide. The new moon is Sunday, August 4th. It's Glenn Fraser's picture of the crescent moon. Next slide. And asteroid number 7, this is the 7th asteroid discovered, Iris, is at opposition, and it's going to be just east of Aquila, the constellation, at magnitude 8.3, and it reaches opposition on August 6th. Remember, this is the fun one with the fun crater names, that Iris is the Greek goddess of rainbows, so its named craters are the colors, different colors and stuff, so they had some fun with it. Next slide. And then we got the Perseids, looking at David Koch's composite here from last year. Really great shot with the Milky Way. It's really known for its bright meteors and colorful meteors. It's been up to, I think in 2016, it was like 200 per hour. So it's got its, you know, it's got its denser parts of the stream. This one, they're expecting it to be favorable, at least from a moonlight standpoint, because what is this? I think this is the third quarter moon or second quarter moon, whichever moon it is. It's a half moon of some sort, and it sets at about 12:30, half an hour after midnight. So that you've got the moon out of the way for when the Perseids get really good, and that's the one you want to watch into the morning. It is material from Comet 109 Swift-Tuttle. Swift-Tuttle is a 16-mile, I didn't know this, it's a 16-mile wide comet. It's an enormous comet. It's the largest object that comes through the inner solar system near Earth orbit. And like sometime in the early 1900s or maybe the late 1800s or something, some astronomer thought that, you know, this was going to be a doomsday comet. This is about the size of the comet that, you know, wiped out the dinosaurs. And so we've got this other character that's in the solar system, and then they studied the orbital data some more and identified that that wasn't going to be a problem until 3000 something. So I think we're good. Next slide. And then August's full moon, so we get to talk about 2 full moons here. August's full moon is August 19th. That's mine. Next slide. Okay, so I just talked about Aquila. So that's the constellation we're going to talk about today. Aquila's not really packed. You know, this isn't Sagittarius, but it's got some cool stuff in it. It's actually known for planetary nebula and globular clusters. since we're pointing in towards, this constellation is in towards the middle of the Milky Way, we're not looking outwards, so it's not really galaxies to be looking at in this constellation. So it's always been associated with a kind of bird, and it was like about, 4th century BC when they started actually identifying it as an eagle. You've got 8 formally named stars. You've probably heard of Okab, but definitely Altair, because that's the bright one in the constellation, and 9 stars with known planets around it. Next slide. So you've heard me rant before about how some of these constellations don't look like what they're named after. And I usually use inthesky.org's map to be my star map when I'm showing locations of the objects I'm talking about. And this is like the stupidest thing I've ever seen. First of all, it doesn't look like a bird at all. Okay, next slide. This is dumb. It's not a popsicle. It's not a cotton candy. I don't know what they're trying to go do there, but next slide. This is, yes? Oh, man. So anyway, the map that I got here is from Sky and Telescope, and look, it looks like the bird. So this person right here attended the day in class in kindergarten when they learned to connect dots. So we're going to use this map because it looks like a bird. Next slide. So the first one is Altair, okay? This is the brightest one in the sky, and I chose this to feature because it spins really fast. It actually correlates with the data that Dr. Yowell had, that hotter stars spin faster. And it's actually so flattened by the rate of speed that it rotates. It takes the light, the equator is farther away from the core of the star, so they call it gravitational darkening, and it's actually darker around. They've actually imaged the star, like imaged the disk. It's not a great picture, but there's an image of a disk, and you can actually see along the equator it's darker because it's so flat. It's this oblate spheroid, and it's like 1.5 times the diameter of the sun, and it rotates one rotation in 9 hours. So in comparison with our 1 million mile wide sun at 25, 26 days, it's definitely not a sphere. Next slide. Then you've got Barnard's E. So this is a dark nebula. I don't usually feature these because it's dark and nobody can really see them unless you're imaging them. But this one's a cool one because it honors Bernard Emerson, Edward Barnard, the astronomer, and he had a catalog of dark nebulae. And next slide, and actually looks like an E. And so it's kind of a cool thing, especially with the dense Milky Way stars behind it. Next slide. And we've got the Snow Globe Nebula. And this one's off to the side of the wing, and you can see the wing because it looks like a bird. It's actually compared a lot to the Ring Nebula because we're actually looking at it from the polar perspective of it as opposed to from the side. And you're looking at a twin-lobed nebula where you're just like looking down the barrel of it. Next slide. And this is a Hubble shot of it, and there's your culprit right there. Next slide. So you've got a pair of globular clusters that are only about almost a little under 2 degrees apart. These two guys right here. Kind of the cool thing about NGC 6760, if you go to the next slide here, not that you can see it, but it's actually got a couple of millisecond pulsars in it. And we're talking about stars that are pulsing they're pulsing energy out of them, and their rotational periods are 5.38 and 22 milliseconds. And one of them has a confirmed planet. This is kind of some crazy thing going on in this globular cluster here. There you go, that guy right there and that guy. So next slide. And then there's the glowing eye nebula. So lots of planetary nebulas. This is kind of a cool constellation if you're into these guys. This is 6751. This is another bipolar in Aquila, and you're basically looking down at in the polar perspective as well. And it's the interesting thing about bipolar nebulae is that their thought, research has kind of indicated that it's because it's a binary star. There's a white dwarf that's creating the expulsion, but that there's a companion that's orbiting it, and that actually influences how the expulsion actually goes out into space, and you get these fun shapes. So that has a lot to do with it. They think that magnetic field has a lot to do with it, and a few other factors. Next slide. And then there's the Phantom Streak Nebula. This makes me want to go to Whataburger because, next slide, it's shaped like one of their it's shaped like one of their hash browns. I really love their hash browns. And the thing is that research suggests that we're actually looking at it from the side. So this is a bipolar planetary nebula. It's a young one, but we're looking at it from the side, and sometimes they're cylinder shaped. So basically, if we were to just rotate this, we'd be able to see down the barrel of it. So that's kind of an interesting perspective on it, where you're seeing a bipolar nebula like this, but it's not that hourglass shape. You're seeing something that's more like a cylinder. Next slide. Okay, and that's it. So more about Aquila. I get my information from the SkyLive. I also get it from Constellation List and these others. But if you really want to do the deep dive into Aquila, and any other constellation for that matter, I suggest it's in volume 2 of the Annals of the Dark Sky, or Deep Sky, features Aquila in it, and it's pretty great. Next slide. By the way, Dennis Webb, who's a member of our club here, is a co-author of that. So keep looking up. I do want to say that this time around, I featured 2 at the end because I couldn't pick between these 2. This is Sean Paul's picture of the Trifid Nebula, and this guy, this is good stuff here. It's a beautiful picture of that, and this is George Lutch's entire shot of the Veil Nebula. So yeah, pretty wide shot there, and a really great one of the Trifid. So thank you very much.
Very good. Yeah, turn the lights back on. Thank you, Bill. So we're going to go into our announcements. And the first one is Bob, do you want to cover the ribbon cutting? Say a few words?
So we had our ribbon cutting 2 weeks ago at lunchtime, and it was an extraordinary event, and it was hot. But I believe we had more than 100 people out there. Most of them from the club. We had many from the local community and the sheriff's department. It was an awesome event. I apologize for being grumpy. I was super tired. But it was just an extraordinary event. Huge table rumble to Mr. Chris Malicki for doing a 4.5 hour live stream from Rising Star. It was our first live stream event out there. We either had over 117
or over 150 people watching from all over the planet, including Poland and Canada. There was one person from Australia. So just an extraordinary event. I'm super proud of Rising Star. It's an extraordinary place. It's there for everybody here to use. And I can tell you that I used the bunk room in the astronomy building last Saturday. It was cool, it was comfortable, and I slept. It was awesome. So it was a great event.
Thank you. So what I wanted to follow up on that was at Rising Star, a Wi-Fi system has been installed. That's the good news. The installation started back in June, and significant progress is made, so Chris could do his thing. That worked out well.
Next slide.
Good. So was Jim going to give it? I was unaware of that.
I only guessed that he was going to speak to it because he spoke at it at the board meeting,
Okay.
but you can,
Okay, great. I'll just finish up.
and you did.
Yeah, thank you. So the plan is going forward. There's a couple of things that need to be finished on the installation of the Wi-Fi system, and we're not going to rush it. We're going to make sure that we get it installed correctly, chase down any problems, get the fixes in place. We're then going to do a soft rollout because how we maintain access to the Wi-Fi system, security, and once those things are properly addressed, then we'll do a full rollout to the membership, to anyone who wants to get onto the Wi-Fi system when they go out to Rising Star. So I just want to let you know things are progressing well, and we have a little more work to do, but we're headed in the right direction. Good? All right. The next announcement is the swap meet.
Yeah, just wanted to say about the swap meet is I guess over the last few years, we've had it in November. And a few people have come to me and said, wow, this is really distracting. I can hardly stand that. I don't know how people do it. Some people came and said, hey, it's like 2 months in a row. We don't get a presentation 2 months in a row because of the Christmas party. So we're going to do it in October. I'm not doing it in August like it used to be because we've got a project scientist from James Webb Telescope coming out, and so yeah, I'm going to leave that one alone.
Is that a big deal?
That's kind of a big deal. So we're gonna work around that and have the swap meet in October, and then November we'll have a regular meeting.
Thank you, Bill. And the last item there is a sneak preview. We will be having a full rollout of the updated logo and some and the FWAS merchandise item. Let's go to the next slide. Oh, looks something like that. So
You lied to me. You said there would be no announcement. Okay. So, good Lord. Okay. Best laid plans.
Oh, your blood pressure's down.
Yeah. All right. So soft rollout. This is actually live, so you can go to that QR code now. Oh, I'm sorry. Now it's me doing it.
Right here. Look at your feet.
Okay. Our merchandise has been up until now on Cafe Press. You probably didn't know that, some of you, because we haven't really ever announced it that much. And the Cafe Press site has been very much unmaintained for a while. So me and actually Michael Tier took it upon ourselves to do a revamp of the whole operation. He had to back out, but he put a lot of work in, give him props. But basically we've been working on this. You can go to this site, it is live. We encourage you to do so. There is all kinds of great branded with our new updated logos on there. I did a cleanup of our official logo. So it's now a lot nicer than it was. And we've got old logos from the past as well in the design collection, and some new designs that I've created in what we're calling the design collection that's in there. There's also some homewares and some other stuff. There will be a kids section coming soon. There will also be some outreach stuff coming soon that will filter into this as it goes. So it will be an evolving project. The design collection will be also rotating. Some designs will be there for a while and then may rotate out, and other stuff will come in because we just don't want it to get super cluttered up. But yeah, go check it out. It's lots of great stuff.
Very good, thank you. Give it to Bill. All right, let's go to the next. While the folks associated with the outreach activities are coming forward to make a presentation or to give a talk, I'll open the field up to any other announcements that we may have. All right, no announcements, so we'll just pass them off to the outreach folks. Come on down.
Hey, next slide. It's up there. All right, so we're in the summer, it's hot, and we're not getting a lot of star parties, so we just have a couple here. So as mentioned in a previous email, we have Space Day coming up at the Fort Worth Museum of Science and History. It'd be a great time to talk about our club, promote astronomy. I know some of you have offered to volunteer for part of the day. It'll be 10 to 4. I'll be there all day. So if you want to help out for all day or just an hour or two, that's fine. Thinking maybe possibly doing a little bit of solar viewing for part of it, and then we'll have some indoor displays. And then if you're not able to make that but want to come down to Cleburne, we'll also have the Star Party down there at the Cleburne State Park. Yeah, I think I got one more. And then I know this is the same night as Tanny Hills, but this is the Crowley Public Library, so they wanted a couple of scopes there. Just maybe 2. It's not a big crowd, so I think we got it covered. And that's it.
Great, thank you, Patrick.
I want to thank everybody for coming out to our July Tandy Hill Star Party. Y'all braved the heat, the wind, and the Saharan dust. So thank you all for coming out. We had about 8 people, 20 to 25 members from the public came out. Next one is August the 10th. The sun sets about 8:18, so we're getting darker a little earlier. Going to have a guest appearance by Saturn, rising about 10, probably 10:15 to 10:20, when we can actually see it above the trees. So one other thing, any person that has a new telescope or is interested in purchasing a scope, come on out. We have all types of this. We have all 3 major types of scopes, and we'd be glad to help anybody that has any questions. Thank you.
Good evening. We're going to have, for July and August, for young astronomers, we're just going to do, I don't want to be in the camera. I don't want to break your camera. So, okay, so we're just going to do star parties. It's summertime, and a lot of the kids are just not around. So we learned a couple of things last couple of months. So on Tuesday next week, 8:45, at the Bedford YMCA. It'll just, we'll gather folks together around 8:45, talk about the program, and then just do a viewing session after. And we'll do the same thing in August. The time determined by sunset. And then we're working with HEB and Birdville ISD to get the word out locally. And then between now and then, we're going to experiment with live streaming from the Bedford Center YMCA so that we can try and find a location, I guess out towards Cleburne, towards Chris Pensick's area, so we can expand the outreach that way and get more kids involved. 1687. Next slide, please. Our next event is this coming Saturday. Yeah, so okay. Yeah, the target group is the Embrace families. That's a group that helps place at-risk foster children and adoptive children and families. There'll be 65 kids out that evening. They provide dinner, starts at 6 o'clock, and then after dinner, the kids are gonna do a fishing tournament, and we'll get set up and start at about 9-ish and go until the kids run out of steam. Patrick has graciously volunteered to come out and help. Could use about 4 more folks and 1 more solar telescope. There'll be 3 more in September, and this is a rain or shine event. So if the weather goes south, Chris Ashford prepares a presentation that we will give that evening. So it's a cool thing, it's a great place, and it's a great experience. Thank you.
Thank you, Bob. So,
Oh, yes, Tom. Yeah, it's in September. I'm trying to get a hold of Katie so I can pass that information off to Michelle, who runs that for the club. And if I remember correctly, for the cottages this year, there'll be a drawing. So, but in September. And that's all I know off the top of my head. Yep.
so we're going to the last 3 reports. Michelle Deason's going to give us an update on the observing area.
While I'm walking up there, I just wanted to thank Sean for the work he's done on getting our merchandise redone. And just because I'm one of those strange people who've been with the club for a while, when he said he worked on the logo, you know, I get sort of weird about stuff like that. Don't touch stuff. But he really just enhanced what we had, because the files that we had were so bad. It was starting to, you know, get that blurry image, like you make a copy of a copy of a copy of a copy. And if you'll notice the old logo compared to the new, I know on the slide that he had up, the logo itself hasn't really changed. But one of the things I think was a really good thing was this little panther that's on here. The new merchandise, the newer logo has a lighter color. So it's a medium to dark gray, so the panther actually shows up better. So thank you very much for your work, Sean. Rising Star Observing Area, we are continuing work out there. I'm volunteering to work on the committee that does maintenance and everything, all the piddly stuff out there. So I know we do have some people who've been doing some mowing for us. Anyone who wants to volunteer to do any of that work, it does not necessarily have to be done on weekends. If you happen to be one of those people who has time during the week and you want to volunteer a little bit of time, you can do that. I know that coming sometime soon, Tom Roth is going to be working on the second deck for the 40-foot container. So he'll put out word when things are organized to a point, he can get a work party out there for a Saturday. Any other information?
Not that I can think of.
Okay, thank you.
All right, Tom, you want to give a talk?
No news right now.
All right, Tom reported that there's no news right now on the Palo Pinto Mountain State Park. Thank you, Tom. Mr. Lutch, are you online?
I am here, sir.
Oh, gosh, okay.
Nothing about the website. As far as media, the newsletter is ongoing, and anybody that has any inclination towards doing reviews or doing any kind of, articles, if you'll just submit them to me and let me know you're going to be doing them. I'll make room for them in the newsletter, and we'll get it done.
Very good. Thank you, George. Next slide. Good. Then we're moving to our financial report. And Constantine's going to give us his first financial report.
Thank you. Thank you, Bruce. Name is Konstantin Bakintas, and I want to thank you for the opportunity to serve as your treasurer. Is he gone? Is John gone? He's gone. Oh my gosh. Okay. Oh my gosh. So I would like to recognize John anyway. He has been serving as our treasurer for the past 5 years. And I'm not sure everybody appreciates, but he's been doing more than just treasurer stuff. He's also been handling all of the membership information. So when he talks about his treasurer's report, it's really a combination treasurer and membership. We had talked, he and I, about actually splitting up today's report where I would do the treasurer and he would do the membership, but it looks like he's gone. I thought he's going to stick around because he said he had 4 trunks of stuff for me to take, so we'll see about that. Anyway, let's talk about where we are. Last month, we had a total of $31,635. There's obviously been some activity. We've had some deposits and some withdrawals. We're sitting right now at $30,966.29. You'll note a line there that talks about a project fund. This is simply some internal accounting that we're doing within our general fund that tracks what's happening at Rising Star. Right now, we have spent $1,334 more than what we had allocated, but it's nothing to worry about. We're expecting some payments for the pads out at Rising Star, the leases, and that'll get us back in the black. So that's moving forward just fine. Looking further on down, you'll notice outstanding Rising Star loans. Those are funds that have been loaned to us at a terrific rate, and I'll have more information on that next month when I get my arms kind of around all of this information and what's going on. But this is simply a loan that is provided by, I understand, one of our members at a very desirable interest rate. So that's a good thing. Moving forward, on to page 2, it talks about our current membership. We had 81% of our members renew, which leaves us right now at a count of 186 Night Sky Network accounts and a total member count of 380. We've already talked about the new members. Thank you for the Johnsons for being here. Moving on to page 3. A little bit of data that talks about how people renewed. I know John was really pushing Zell. As long as you renew, we're happy. So moving on, the bottom of that page 3, I think is critical to understand what's happening. It's important to appreciate that membership has grown steadily since 2020, when everything came to a halt. Right now, our largest Night Sky Network account was 222, and that was right before the renewal. We had a number of people drop, and the following page, I believe, is the graph that shows what's transpired over last July through this July. Last year, we had a maximum of 201, and there was a substantial drop. It's actually sharper than what the graph shows. And this year, we had a high of 222, and after the drops, we're down to 186. That is a quick summary of what I had to say this report, and I'll have more information as I get my arms around all this information, all these different accounts and everything else that's going on. Thank you.
Thank you. I'm not aware of any infrastructure or legal issues, especially with Cy not here, so we'll move on to the next one. Other business, like we showed earlier, we had a number of members. What was the number? 380 members, people involved. And the bylaws calls for 3 standing committees. So I worked this year and I made 3 appointments to that. I made 3 appointments. I offered those positions to 3 people and I got yeses. Like Michelle said, she took the observing area committee, so I'm pleased with that, and she'll spearhead the maintenance and other activities out at Rising Star. Just tonight, I got Maru, whose last name I can't pronounce, and my apologies to him, who accepted membership. And so we've taken both membership and the treasury away from John Giramani, and so he can start to unwind. No more emails at 1 a.m. I'm pretty pleased at that. And the last committees are our outreach committee, and Christian Penzick has accepted that position to spearhead that. So I'm happy with that appointment as well. So I just want to let you know that those positions have been filled, and the whole idea is that share the work, make this more effective operation with less work on my part. So I'm really pleased with that. Any other business to bring up? Next slide, then.
Okay, so next month we've got Dr. Dan Davis. This guy's great. I saw him speak at the El Dorado Star Party during the annular eclipse. He came out and he talked about tectonics around the solar system, and it's fascinating and it's entertaining, so it'll be a good one.
That's great to hear. Next slide. As usual, there's an after meeting gathering at the Social House right down the street off of Camp Bowie. I've never been to one. I can't make tonight, but I understand it's a good deal. So as we heard, our next meeting is August 20th, and I'm now looking for a motion to end the meeting. Motion to end the meeting. All right. Do we have a second?
Second.
Okay, all those say yay.
Yay.
Okay, that's it, carries. Good night.